Miruna, over to you now.
Hello, everyone. Thank you very much for this opportunity. I'm happy to present here these lectures. I am sorry I am not in person there with you, but it's good that I can attend online. I also saw last week week 0, and it was very interesting. And yes, I hope this will work out well. So this is the first lecture. Can you hear me well? I hope it's fine. Okay, thank you. So I will talk in these lectures about these guys, historic dynamical systems. Try to see how working. So these guys, historic dynamical systems. This is the goal for these lectures. Right now, just 5 minutes, I will talk about the big picture, what we plan to do during these 4 lectures and 2 tutorials. But then today's goal will be slightly different, will be elimination theory in action. We'll see some very useful techniques that I will need in introducing these guys' historic dynamical systems. So here, for the references, I will give references during the next lectures when I get to it, to this topic more in detail. And you can find also in the abstract on the webpage of the SIMPA Research School. So this is going to be a very interdisciplinary subject because it comprises both nonlinear polynomial dynamical systems and nonlinear algebra. As you know, this term that was coined recently, that is under it, it's an umbrella for applications of algebra and algebraic geometry, combinatorics, computational algebraic geometry. Okay, we'll also sometimes encounter linear algebra, of course. So what we want to do is to discover qualitative, to study qualitative properties of what are called complex balanced. I will introduce this terminology in the next days, but I'm just saying quickly that we are interested in qualitative properties of complex balanced mass action systems. And some of these notions you will probably already see tomorrow during Beatrice's lecture. We'll see. There might be common notions appearing, which is good. So qualitative dynamical properties of this kind of dynamical systems, and actually these are also called toric dynamical systems. These are the ones that we are interested in. So actually it represents this class represents a family of polynomial dynamical systems. So here is where algebra and algebraic geometry you can already see come into play. And moreover, these polynomial dynamical systems that are inspired by reaction networks. So you can also think of interaction networks. or biochemical reaction networks. So it's here is the connection with the applications, but reaction networks in general, where by networks we mean these are some graphs, and I don't define them now, but we will see. And you might wonder also why we want to work and study these special family of dynamical systems. And here I mention quickly two reasons. First reason, because these systems are known and sometimes conjectured. We will see why I say this, conjectured, to enjoy very nice dynamics, so like long-term dynamical properties. Long-term dynamical behavior is very nice. One reason, and the second reason why we want to study them is the fact that we understand and we can use easily their algebraic structures. And right, this will be more clear later on. So we understand their algebraic structure. So under some algebraic conditions, we can deduce there is some nice property of their dynamics and so on. This makes you, just to understand, this is the reason why they are called toric. We'll see. And the tools we plan to use throughout these lectures, some of the tools, we also use combinatorial tools, graphs. Already the network is a graph. So these are combinatorics. But of course, ideals and algebra, and here especially we will be interested in elimination. We will have this tool, elimination theory. Then since these systems come from applications, there are real coefficients coming into play. And concentrations and so on. There are so the real side of algebraic geometry comes into play. So real algebraic geometry, theorems, tools, and so on. Maybe here I just say a couple. For instance, the discriminant that we will see today. Descartes rule of signs, etc. And maybe I mentioned also an important thing we are leveraging in the proof, which is dynamical equivalence. But we'll see what this is, of course, just to have an idea. Okay. So to this end, today I plan to focus on elimination theory, some aspects of it, and I know that this was already introduced somehow briefly last week, but we go into more detailed explanations and examples and theorems. We will also use Macaulay too at some point, just for to get an idea of how it works on that online website that you already used last week, so that during the tutorial session we can take advantage of it and work some more exercises. So today, at least today, we plan to work on elimination. Right, so elimination theory, which is anyway a good tool in it's a good toolbox to have for applied algebraic geometry, applied algebra, not only for these lectures in particular. So the structure today will be, I start with just some examples to give an idea what it helps us to do elimination theory. Then we will treat the univariate resultant and the discriminant. And if time, we'll see how much time allows, we will talk about mapping and projecting. So the Gröbner basis approach in elimination theory, which actually will help us later on to compute some moduli space, some parameter space for the toric dynamical systems. Okay. So I'll start with an example. I will call it hyperdeterminants of tensors and singular surfaces. In C3, let's say. So for a while, I give here as a reference, I will focus for a while on a book that I recommend you to read. This is called Invitation to Nonlinear Algebra. I mentioned it in the abstract, so you can find there the details. So by Mihalek and Sturmfels. Here you can find these examples, some of the things I'm saying in what follows. Sorry. So what I mean here by this example, so hyperdeterminants of tensors. I want to say that in linear algebra, you know, of course, that we usually play with the matrices. So I want to make a correspondence, and in nonlinear algebra, at least now, the equivalent or the correspondent of matrices will be tensors, and just in this example, we are looking at these. So if in linear algebra we encounter the determinant of a matrix, in nonlinear algebra, the key tool is the hyperdeterminant, so-called hyperdeterminant. Okay, so let's see. So I don't go into many details about tensors, but there is a whole chapter about it, about these objects in this book. Very interesting, and they are fundamental objects currently, for instance, in data science. They appear in many branches of mathematics. So I didn't say tensors are multidimensional arrays. Okay. Okay, so let us consider x I, j, k, a tensor of format 2 by 2 by 2. Okay. So here 2 by 2 by 2, this gives us 8 variables. These are the entries of this tensor, and we can consider this as a cube. I won't draw very. Okay. And the vertices of this cube can be labeled I won't write x, I just 0, 0, 0, 0, 0, oh, sorry, let's write 1, 0, 0, 1, 1, 0, 1, sorry, 0, 1, 0, and 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, for instance. Okay. And in this whole example, we just consider that x is actually an element of the 8-dimensional vector space where we have a basis indexed with this ijk. So this is an 8-dimensional linear space. In this case, x gives us actually, so we can say that the tensor, just to not get into more other theories, we just think in this example that the tensor represents a polynomial in 3 variables. Let's call them Z1, Z2, Z3. How does this look like? So we have the tensor, okay, and we have f, this is the polynomial, x0, 0, 0, plus x1, 0, 0, 0, 0, Z1, plus x0, 1, 0, Z2, plus x0, 0, 1, Z3, plus x1, 1, 0, Z1, Z2, plus x1, 0, 1, Z1, Z3. Of course, here you notice the index tells us which variables from the 3 Z1, Z2, Z3 we consider in the monomial, plus x0, 1, 1, Z2, Z3, and plus x1, 1, 1, Z1, Z2, Z3. So now, for a fixed x, for a fixed vector here of this 8-dimensional space, this polynomial defines a surface that lives in C3. And now the question that we are going to answer using elimination theory will be, when is this surface singular? So when does this surface fail to be smooth? At some point in C3. So we have the following question. For any fixed x, this polynomial defines a surface V of f in C3. And now comes the question, when is this surface singular at some point Z in C3? So we want to know for which values of x, of capital X, the surface given by then this f that is now a fixed polynomial is singular at some point Z1, Z2, Z3 in C3. Preparing ourselves to get to this ideal world from last week. So the variety here given by f is singular at a point Z in C3 if and only if the pair x, it's 8 entries and Z with 3 belonging to C11 lies in the variety given by this idea. Let's see which is this, where I is the following. So is the ideal generated by F. And of course, because we are interested in the singularities of the surface, we want that the partial derivatives with respect to all the entry, with all the Z1, Z2, Z3 to vanish. So this is a part. We are almost ready to get to an answer. So when we are interested, when does there exist some Z in C3 such that the surface is singular? So in this case, what we want to do is to eliminate, and we can make this more precise in what follows. We want to eliminate precisely Z1, Z2, Z3. So you can think of it as an existential, you can think in terms of quantifier elimination, for which X, for each which X here, does there exist a Z that satisfies the fact that the pair lies in this variety. So what we do, and we'll see this more theoretically soon, is that we eliminate Z1, Z2, Z3. So we consider the elimination ideal, J, which will be this previous ideal, where we intersect it with C of the variables, only the variables X. Okay, and what is interesting is you can already once we learn how this works in practice with Macaulay 2, you can do this effectively. But now I will give you the answer, because I think it's also a very interesting object, this answer. It's nice to find it, to meet it. So the answer is that this J is a principal ideal generated by the following polynomial H as follows. So the polynomial is a long polynomial, is an interesting combinatorial object, because we can think of the cube from before. And we had these entries. Let me write them again. This is a nice way to remember, and since I like it, I wanted to share it with you. It's a nice, the cube will tell us how to remember the result of this computation. So we will have, let me write first part. So for instance, we will have x110 squared, x001 squared plus. So we see 110 here and 001. This is a long diagonal. This is a long diagonal, one long diagonal, and you take the squares. Then we have x100 squared, x011 squared. So 100 and 011, another long diagonal. Plus, we have two more, x010 squared, x101 squared plus x000 squared, x111 squared. These are all the diagonals, so 0001111, and the last one 010, and this. Okay. These are some terms of this polynomial that we are interested in. And then there are, let me write with another color. There we have 4 times. Let's write x0, 0, 0, x1, 1, 0, x0, 1, 1, x1, 0, 1. And if you check these 4 vertices, so 0, 0, 0, 1, 1, 0, 0, 1, 1, and 1, 0, 1, these points give us a tetrahedron. Okay. And like this, we will have one more tetrahedron here, x010, x100, x001. Okay, maybe I will not write all the terms, but just I want to mention the last ones, last type of terms we have here. Sorry, this is minus 2 times. And here we have rectangles slicing the cube. So x, I'll write just 1, 0, 0, x1, 0, x0, 1, x0, 1, plus, and so on. These are rectangles slicing the cube. This is 1, 0, 0, 1, 1, 0, 0, 0, 1, and 0, 1, 1. Here is a rectangle. And so this I want to present this example because I find it very interesting, since it is a known polynomial that's called the Cayley hyperdeterminant. And you can maybe it's also an invitation for you to read more about it in this book, Invitation to Nonlinear Algebra, but in another chapter that's about invariant theory and so on. Okay, so why we compute this? Just remember, we wanted to eliminate these variables, and we said that the new ideal, this elimination ideal, is generated by this polynomial in the entries of x. Okay, so essentially, the conclusion that comes from elimination theory is that h, this polynomial, is 0 when we have that this v of f, the surface from before, is singular in C. So if the entries of capital X verify this equation h equals 0, we know, I mean, when the surface is singular, we know that the entries will verify this polynomial. So this was just an instance of using elimination theory to compute or to decide whether a surface has singularities or not. Let's see, maybe some other example. This was a long one. Let's see another example. That we can also apply in Macaulay 2 just now. So let's say implicitization. We call it this example, implicitization of a rational curve in the plane. And here I can recommend as a reference solving polynomial equations. It's a book by Bernd Sturmfels. So this example is meant to show us in practice something that we saw also last week quickly, but I want to also make Macaulay 2 example so that during the tutorials we can solve some more exercises in this manner. So let's write what we want. So we consider C a plane curve, okay, and given parametrically, so given by the parametrization, C is, we write it like this. Let's write. Let's consider polynomials in T, A of T, B of T, and we have C of T, D of T. You can think of it in A squared. Okay. So T is, sorry, T is a real number this time. B, C, D are polynomials. Let's take them in this polynomial ring with coefficients in Q. So what we want to do is to, our goal is to find the unique, irreducible polynomial f. So into variables, with rational coefficients, which vanishes on our curve. And we will use in this example two methods. So I insist with this first lecture, even maybe it's known, the theory is known, but I want to make sure that these computations are known, because I encountered very often in solving polynomial dynamical systems, this approach is very useful in many projects. So the first one, the Grosvenor basis approach, we'll see, and the second one is the univariate resultant approach. But I will choose now precise polynomials A, B, C, D, so that we have this parameterization. Say A, we can consider, let's say, t cubed minus 1, B of t, say it's t squared minus 5, C of t is t to the fourth minus 3, where and d of t is t cubed minus 7, to have concrete parameterization. So what is the first method we can use here? So you see, this will be our x and our y. So x is a over b, and the y is c over d from this writing. Okay, so now just as an example, later we'll see the theory, how to compute f of xy. So this will be given by the resultant in t of, I told you, a over b equals x. So we have b of t times x minus a of t. This is vanishing, and I mean, we want this to happen. And then for the second one, d of t times y minus d of t times y minus c of t, to have resultant in t of this set of two polynomials. And this will give us, we will see now with Macaulay 2 how it works. Essentially, this will be the irreducible polynomial that vanishes on our curve. And the second method will be using elimination ideals. Okay, so here, directly with elimination ideals, we'll see in Macaulay 2. So maybe you can keep this in mind if you wrote down these polynomials, because now I will stop sharing here, and if possible, let's see. I can stop sharing. I don't know how to. Maybe I can try to share screen directly here. Can you please allow me to share on the other Zoom account? Thank you. Okay, it works. So let's see concretely how to get these. So remember, we have the parameterization, and we want now to find the polynomial that vanishes on our curve, polynomial in two variables. Let's try to use the resultant method. So of course, I didn't say the whole theory, but I wanted to show in action some examples first. So let's see first case. We define our R. So here we have a, you saw before, as I wrote, we had a polynomial. We have a resultant in T, okay, and we are interested in obtaining the implicit equation in X and Y. So here we start by taking the coefficients, polynomials in X and Y, and we work with the variable T. And F, now we will, okay, we call it F, we can call it G, for instance. Sorry. G will be a set of polynomials that we want to consider. In our case, these are the two polynomials from before that I had written. That was B of t times x minus a of t. In our case, we have t. So B of t was t squared minus 5 times x minus a of t. A of t, I chose t cubed minus 1. Okay, and the second equation we want to consider d of t, so it was t cubed minus 7 times y minus t cubed minus 7 times y, and minus c of t, which was t to the fourth minus 3. Here we defined this list. It was already expanded for us, and now I hope you have this package. So we add load package. Maybe it works also without, but I need to load the package for the resultant to make sure that my command works. Oh. Maybe I should. Okay, sorry. Resultants. Okay, so now we want to compute, and we'll see that later, maybe in another lecture, we'll see how to make it also by hand, but with Macaulay 2 is just rapidly find resultant, and we place here the set of polynomials introduced before, and here it gives in this way we obtained the polynomial that vanishes on our curve. You can see it here. So this was the first approach. And I went a bit quicker because I know that you discussed this last week, and that's why I didn't want to get into all the details, because I wanted to present also the elimination approach. So let's give a reset. Now work with an elimination ideal to see if it gives the same implicit polynomial that vanishes on our curve. So take R. In this way, here this second approach is based on lexicographic elimination. So let's take this ring. We have T. Denote our ideal I, where we place. And here I can just take the polynomials from before, just to copy. They're the same, of course. We want to define this ideal that is generated by these two. This is I, so taken from the parameterization or curve. And now another way to do this, which works more generally, okay, than the previous one, is the following. So we want to eliminate T from these two equations. For that, we use eliminate command. We write here which one we want to eliminate and from which ideal. So this is actually doing computing the elimination ideal. And so we can compare now and see if we got the same thing. And actually, so okay, here this is the ideal generated by the polynomial. But note that actually this is, so the above polynomial is just twice this one. So everything is going on well and nice. So with these two methods, we saw how to compute concretely, and it will happen. We will exercise more during the tutorial session. We will apply these in completing the entries of some matrix with several properties or so on. Stop sharing now and see. I can share my screen from the other. Okay. So these were concrete examples. Time to see some theory. The first one we will consider, and that's the first part, is the univariate resultant and the discriminant, which the discriminant is a special case of the resultant. And this, why I want to present the theory about this, because I need the discriminant in the paper I'm going to present in the next lectures. So we need to know this notion. So the example parts is done. We can go to the univariate resultant and the discriminant. So what's the goal of the resultants, or what do we want to do with this tool? In algebraic geometry, one often has to decide whether two polynomials have a common zero or common zeros. And the resultant helps us to read these from the coefficients of the polynomials. Okay, so we don't need to determine the zeros, but we can check that the two polynomials have common zeros just by looking at the coefficients of the two polynomials. So goal, decide whether two polynomials have common zeros. How we do this? As I said, we can read this from the coefficients of our polynomials. So without determining the zeros. Let's see more exactly. Let's take R, some commutative ring, say with unity here, and we take two polynomials. We work here with two polynomials. Let's say f is a0 x to the m plus am. So this is in the ring polynomials with one variable x, coefficients in our ring, R, and G, let's write b0 x to the n plus bn, again in this ring of polynomials. So we have these two polynomials. What we want to know is if they have common zero. But what will help us discover? This is the resultant. Let's say we denote, let's say, I write this like this, resultant index x, because we will obtain a condition in terms of the coefficients of the polynomials f and g. So let's first define these. So what we do, we take a determinant of a matrix where we place in a precise manner the coefficients of our polynomials. So let's write like this. This is the determinant symbol, and we take first n rows. We write the coefficients of the first polynomial. Okay, so we have a0, a1, am, a0, a1, am, and so on. The rest of the entries are 0, and here am, and somewhere around here we have a0. Okay, these are the first n rows. And the rest of the entries, as I said, are 0. Everywhere is 0. And what we do is with the next m rows, so this will be this matrix that has m plus n rows. We place the coefficients of the second polynomial, b0, b1, somewhere here it's bn, and so on. Here we have b0, b1, bn. This is called the Sylvester matrix. I mean, this is the determinant of the so-called Sylvester matrix. Because let's see how much time. Not much time. Let me write for our case where we consider the result, the polynomials where R, no, sorry, just a second. I'll skip a bit of this part and go directly to the corollary that we are interested in and that we already used in Macaulay 2, and actually it's based on this theory. So we have the theorem what does the theorem say? Well, it says that f and g, these polynomials, we're considering R to be the complex numbers here. They have a common 0. Okay, we need to assume that both have degree at least 1, so that we don't encounter problems. But f and g have a common 0 if and only if the resultant vanishes. So let's write this rigorously, and then we will see more details. So for f and g, I wanted to make the general scenario, but maybe in the interest of time, I just go to the corollary that I had. So if we consider polynomials with complex coefficients, where the degree of f and the degree of g is at least 1, the following are equivalent. So as I said, first is that f and g have a common 0, and the second one say that the resultant of f and g is 0. This is one of the main results for this section of the univariate resultant. Essentially, as I said, this resultant gives us conditions in the coefficients of the polynomials. You see, this is it has a determinantal shape, this polynomial, such that the two polynomials have a common 0. And then let's see how to compress a bit this part. And now I also want to say, if I have 3-4 more minutes, I'd like to say a few words about the discriminants, since we will be using it later. So if we take a special case, so essentially where g is the derivative of f, so if we have f, let's write formally, an x to the n plus a1 times x plus a0, again, the general case with this ring, and f prime, we consider n times an times x to the n minus 1 plus a2 x plus a1. We give a definition. So given these two given f, okay, and f prime, the formal derivative of f, so that by definition, the discriminant of f, let's write it, for instance, d index f, is the resultant of f and f prime. Okay. This is called the discriminant of f. And now, of course, you can quickly think of the connection between, of course, f and f prime having a common 0 and the discriminant. Okay, so essentially, we use the discriminant to detect when a polynomial has a multiple 0. In this case, for us in C, we are interested to work in the field C. So let's write directly the result I want to finish with. This is a theorem that for, let's take f in C of x, the following affirmations are equivalent. I write briefly then. F has a multiple 0 in C, and the second affirmation is that the discriminant of F vanishes. During the tutorial session, we will work with discriminants and see concretely for a theorem in the context of disguised storic dynamical systems, how this discriminant helps us separate multistationarity and unique equilibria, so parameters that give different dynamical behavior, and it's I will stop here because I think it's time. Thank you very much.
Okay, thank you very much, Miruna. Probably there are no questions at the moment, but definitely you mentioned a few good references, and along with these slides and the recording will be uploaded on the web page. So probably we may expect many questions next time. Thank you. Thank you very much, Miruna.
I am happy to answer any questions on Wednesday. Yes.
Yeah. Okay. Thank you.
Thank you.
Okay. Now, there is a tea break. Let's make it a bit quite interactive. So along with the tea break, make it a bit short so that we can